Okay, welcome to Chapter 17, Section 2 on current. Let's get right to the key ideas here. How are electrical and potential energy, how are electrical potential energy and gravitational potential energy similar? What causes electrical resistance? So, start off, voltage and current. How are electric potential energy and gravitational potential energy similar? So, just as a ball will roll downhill, a negative charge will move away from another negative charge. So it'll move away. We know that like charges repel each other, so if there's two negative charges, they will try to move away from each other. If one is fixed, it will push the other one away from itself. So electric potential energy is the ability to move an electric charge from one point to another. So the potential energy of an electric charge depends on its position in an electric field. The electric potential energy of a moving charge decreases because the electric field does work on the charge. So you have electric potential energy here in comparison to gravitational potential energy. So more gravitational potential energy is like more electric potential energy, so the farther distance you get away, it has less gravitational potential energy here as it does here. There's less electric potential energy here. So the closer that negative charges are together, the more electric potential energy there is. The farther away they are, the less there is. So potential difference is measured in volts. The definition for potential difference is the voltage difference in potential between the 2 points in a circuit. It's hard to measure potential energy at a particular point, but it's a lot easier to measure the difference in those potential energies between 2 points. So that's what we actually measure as voltage, is the electric potential difference between 2 points, not the actual electric potential energy. So for a repulsive force, electrical potential energy increases as the charge moves closer to each other. The volt, which is the units we have for potential difference, represented by a capital V, is equivalent to 1 joule per coulomb. And potential difference is often called voltage. So looking here at, you have lesser distance, you have a high electrical potential energy, you have a fixed point of positive charges here, and you have a close positive charge which will repel, so there's a lot of potential energy there. Low potential energy because it's wanting to attract to this, not go away, so the very low potential energy associated with here. If you have greater distance with a positive, you have a lower one. With a negative charge, you have a higher, because it is attracted more to that positive area. So let's watch a little video here on electric potential energy.
When two charges interact, they exert an electric force upon one another. The potential energy associated with this force is called electrical potential energy. It is a form of mechanical energy that increases as the magnitude of the charges increases, and decreases as the distance between the charges increases. In a uniform electric field, the electrical potential energy of a charged object is due to its position with respect to the direction of the electric field. Displacement of the object perpendicular to the electric field does not change its electrical potential energy. Charges that are allowed to move freely will move to positions of lowest potential energy. In the device shown here, electrons exit the central sphere and move to the outer sphere. As this happens, the electrons lose electrical potential energy in exactly the same way that a falling object loses gravitational potential energy. If a person touches the outer sphere, the charge can then pass from the sphere to the ground, where it reaches an even lower potential energy. Charge naturally flows in the direction that results in the lowest electrical potential energy.
Alright, let's continue on here. So a little more about potential difference.
Potential difference. The potential difference between any 2 points is the work that must be done against electric forces to move a unit charge from one point to another. Potential difference is expressed in volts.
Okay, so you have like terminals of a battery, like a positive and negative terminal on a car battery. The 12 volts is the amount of, represents the amount of work or energy that must be done to move a charge from one pole to the other. Alright, so let's watch this video on voltage.
Voltage is a measure of electrical push. A higher voltage will cause more energy to be released as a charge moves through a circuit. Batteries can have different voltages depending on how they are made and the chemicals they contain. Even batteries with the same voltage are not identical. Each of these batteries is rated at 1.5 volts. But only several large batteries contain enough energy to power a large stereo. Voltage is not the only thing that matters when you are trying to power an electric circuit. Current, energy, and power are all important too. Still, you should probably not ignore signs like this.
Alright, so voltage and current. There is a voltage across the terminals of the battery. As long as you connect across the terminals of the battery, there is voltage. If you just measure one terminal, there is no voltage across because you haven't completed a circuit. You have a thing called a cell, which is a device that produces an electric current by converting chemical or radiant energy into electrical energy. One terminal end is generally a positive end, the other terminal is the negative end. And generally batteries convert chemical energy into electrical energy. In this particular case, you have a filament with a NiCad battery here. You have the positive.
Batteries contain one or more electrochemical cells. They use the energy from a chemical reaction to generate electrical energy. Batteries consist of at least one anode and at least one cathode. Batteries contain one or more electrochemical.
Alright, so an electric cell here.
The purpose of any type of electric cell is to increase the potential energy of the electrons passing through it. A battery consists of one or more electric cells that convert chemical energy into the potential energy of electrons. Chemical reactions transfer electrons in the battery from the positive terminal or anode to the negative terminal or cathode. Like other types of electric cells, batteries maintain a potential difference between their terminals and thus are sources of electric current.
Alright, so a voltage, basically what it does with the difference in potential energy there, it makes charges move. So it sets those charges in motion. And when we talk about current, current is the rate of charge movement, or how many charges are moving in a unit time. Kind of like if you go out and count the number of cars that go by you on a road, that would be a rate of cars in motion. In this case, we're talking about the rate at which charge passes through a given point, and that's called electric current. The SI unit of current is something called the ampere. Sometimes it is abbreviated as amps. It's represented with a capital A. This is the unit of current. It is different than an amplifier, which is sometimes called an amp, that is used in car stereo systems. That's a different thing altogether. As far as an amp is concerned in electricity, an amp is equal to a coulomb per second. That means 1 coulomb of charge has moved by in 1 second time period. So you have a couple different types of current. You have direct current source, where the charges always move from one terminal to the other terminal and always in the same direction. They stay in one direction, they move in that direction from one terminal to the other, and that's always the case. Example of those are batteries. Now you have conventional current, which is current made of positive charges. We actually know that electrons flow from the negative terminal to the positive terminal, but conventionally, or basically in tradition, is that the flow of positive charges is what constitutes conventional current, which would be positive charges going from the positive terminal to the negative charge terminal. So the current made of positive charge, that would have the same effect as the actual motion of charge in the material. So the direction of current is opposite to the direction of that the electrons move. So let's watch this comparing direct and then something called alternating currents.
Current is the rate at which electric charges move through a given area. There are two types of current: direct current, DC, and alternating current, AC. In direct current, the current moves in only one direction. In alternating current, the current reverses direction at regular intervals.
Okay, here, so you can see in direct current, again, all the charges flow in one direction, and they always flow in that one direction. That's where you have the current is going in, is a positive value over a given time period. But in alternating current, the charges go back and forth and back and forth and back and forth. That's why you have this positive, negative direction, negative direction, positive. Goes back and forth as it goes through the wire. So let's watch this one on conventional current.
Electric current is the net flow of electric charge carriers from one point to another. The charge carriers can be negative, positive, or a combination of the two. Which is the case is not a concern for most applications. For this reason, scientists have chosen to treat most electric currents as if they were entirely due to the movement of positive charges. This equivalent current is referred to as conventional current. For many applications, it is not important whether the negative charge carriers are moving in one direction or the positive charge carriers are moving in the opposite direction. In these cases, scientists treat electric current as if it were entirely due to the movement of positive charges. The conventional current is a current that has the same net movement of positive charge as the actual current. In the case of a current within a metal, the actual current is due entirely to the movement of negatively charged electrons. If the electrons, which are negatively charged, move from right to left, the conventional current is an equal amount of positive charge moving from left to right. In particle accelerators, currents can consist entirely of moving protons. In this case, the conventional current is the same as the actual current. In some gases and dissolved salts, current can be due to positive charges moving to the right and negative charges moving in the opposite direction. In this case, the conventional current would consist of positive charges of an amount equal to the total movement of charge, but all moving to the right.
Okay, so let's talk about electrical resistance. What actually causes electrical resistance? Basically, resistance is caused by internal friction, which slows the movement of charges through a conducting material. So resistance defined is the opposition presented to current by a material or device. And what actually happens there is electrons are actually bouncing into, kind of like a pinball machine, they're bouncing off of the atoms that are located in the material. And as they bounce around, that's what creates the resistance. That doesn't allow them to get through the material as quickly as they could. So resistance can be calculated if current and voltage are known. A conductor's resistance indicates how much motion of charges within it is resisted because of collisions of electrons with atoms. So there's something called Ohm's law, which is developed, which is a relationship of voltage to current. And that gives you the resistance. So resistance is equal to voltage divided by current, and we shorten that up in symbol form to R is equal to V divided by I. The units of resistance is the ohm, which is a Greek letter omega, kind of looks like a funny horseshoe, and that's equal to 1 volt per ampere. A resistor also is a special type of conductor that's used to control current, and it has different amounts of material inside the resistor so that it resists at different values. So some math skills here. The headlights of a typical car are powered by a 12 volt Battery. What is the resistance of the headlights if they draw 3 amps of current when turned on? So we list the given and unknown values. Given we have that the current is 3 amps. The voltage is car battery, so it's a 12 volt battery, and unknown to us, which it wants us to find, is what is the resistance in ohms. So we write the equation. Resistance is voltage divided by current. We insert what the known values are. So in this case, 12 volts is the voltage, 3 amps is the current, and that gives us a resistance of 4 ohms. Alright, so conductors generally have low resistances, and insulators have very, very high resistances. And then you also have things called semiconductors. And semiconductors only conduct under certain conditions. Semiconductors defined are materials that have electrical properties somewhere between those of insulators and conductors. Some materials can become what's called superconductors. Some metals and compounds have zero resistance when their temperature falls below what's called a critical temperature. Usually it's an extremely low temperature, the minus 200 to 400 degree range Fahrenheit, so it's extremely cold, what we figure. And a lot of times when they've developed those materials, yes, they have zero resistance. If you actually induced a charge to flow in those materials at that temperature, that charge would flow continuously uninhibited or without resistance for infinity. Basically, it could go on forever and ever as long as it stayed at that temperature.